Okay, so welcome. So we have been discussing various aspects of two-dimensional NMR. We have spent a couple of lectures on discussing the COSY and its variants, various kinds of issues in the COSY. Especially just to remind you, in the COSY spectrum, we had the cross peaks and the diagonal peaks. The diagonal peaks had the dispersive character and in-phase character. The cross peaks had antiphase character and absorptive line shape, but they have positive negative signals, as I would like to say here once more. Draw the cross peak pattern here for a two-spin system. Then you had this. And this, because of this positive negative character, we had cancellations of intensities. So that will result in reduction of the intensity of the cross peaks. In the diagonal peaks, we had this sort of a situation. This is the cross peak and this is the diagonal peak. We had in-phase peaks, but they were dispersive in character. So therefore, it used to add in a way that we lose resolution in the spectra. So to circumvent this problem, we also discussed a new variation, and that is called the double quantum filtered COSY. In the double quantum filtered COSY, we had, so in DQF, we had this sort of a character for both diagonal and cross peaks. This is in DQF COSY. We had this character in both, and also they all had the same absorptive line shape. So therefore, this resulted in a substantial improvement in the cross peak in the resolution. And subsequent to that, we also did what is called as the constant time experiment. In the constant time experiment, constant time COSY, this is CT COSY. Here, we removed the coupling along one of the dimensions, that is the F1 dimension. Therefore, we had only things like this. We didn't have the coupling displayed on the second in the F1 dimension because we decoupled in the F1 dimension. The coupling is still available in the F2 dimension. That is this is the F2 dimension. Coupling is still available here. So we can measure the coupling constant. But sometimes when you want to measure the coupling constant, you need to have very good resolution. And if the resolution is not very good, then you may lose you make a wrong estimate. So you may make a wrong estimate. Why it happens like that? Let us consider this situation here. You have an absorptive peak here and a dispersive, not dispersive, another absorptive peak which is going like this in the negative dimension. If there is a cancellation of the intensities of this, the peak center which is here and the peak center which is here, they may get shifted away slightly, and then you will measure a coupling constant which is wrong. So therefore, you have two objectives here. One is that to measure the coupling constant accurately. Second, you reduce the cancellation of intensities so that you get better cross peak intensities. So this is what is being achieved in this new set of experiment, which is called as the scaling in two-dimensional NMR. You bring the concept of scaling so that you can change the coupling constants artificially. Not that you change it in the actual molecule. The coupling constant remains the same. But the way it appears in your spectrum, you want to change that so that your measurement will be accurate and the intensities will also be very good. So this is the pulse sequence which achieves this purpose. Okay. To simply looking at it, what we have done here is a simple modification of the COSY pulse sequence. The COSY pulse sequence had only two pulses, 90x and 90x, and there was a T1 in between. Now what you do is you introduce a spin echo sequence here. This is a spin echo sequence in this. This is the tau 180, tau 90 spin echo sequence. So what happens during this period? The chemical shift gets refocused. Okay, chemical shift is refocused, but the coupling constant is not refocused. This we have seen in the spin echo. When you're talking about homonuclear experiments, proton-proton experiments, for example, the proton-proton coupling is not refocused, but the chemical shift is refocused. Therefore, the chemical shift evolves for the period T1 during this, in the entire pulse sequence from here, from 1 to 4, if you see, the chemical shift evolves for the period T1. Here only chemical shift is evolving. Now, where the coupling constant evolves for the entire period, all the way from 1 to 3, okay, from 2 to 3. 2 to 3 coupling constant is evolving. Because it evolves in T1, it also evolves in the spin echo sequence. Therefore, artificially, you have allowed different evolution times for the chemical shifts and the coupling constants. But the Fourier transformation does not know that. So as a result of that, what will happen is in your spectrum, the coupling constant appears scaled. That is a trick here. So objective is to scale selectively either the coupling constants or the chemical shift. In this thing, what we have shown is this, how we manipulate the pulse sequence parameters to achieve the scaling of either the coupling constants or of the chemical shifts. This I will show you in the few slides. It will come. Okay. So these are the purposes. One is you want to minimize the cancellation of the intensities by increasing the separation between the components. Okay, so that the cancellation does not happen. Secondly, when you increase the separation between the components, you can actually measure the separations also quite well, because the separation represents the coupling constant. So you can measure the coupling constant. Very small coupling constant, if you want to measure something like about 0.3 hertz or 0.4 hertz, your line widths are usually much larger than that. In such a situation, you can't get this measurement accurately done. Sometimes you may have to scale therefore by 10-fold and 20-fold. And there was one case where the people even scale 90-fold. Okay, that was to measure the coupling constant. In that situation, this becomes extremely useful. But the idea is demonstrated here with a simple example. I will show a simple example for a homonuclear system. Okay, so the pulse sequence we have again the 90, 180, tau. There we have a spin in the spin echo sequence introduced in the middle after the T1 evolution. Then you have the spin echo sequence tau 180 tau introduced, and then you have the final 90-degree pulse, and then you detect as a function of T2. Now the tau is adjusted to be as proportional to T1. It is a tau is equal to alpha times T1, which means as we increment the T1, this tau also gets incremented. Okay, so from every experiment to experiment, when you are performing different experiments, tau also keeps changing. As you change T1, the tau also changes. Okay, and that is how you will achieve the scaling of the coupling constants. Okay, so let's see in the next slide how does it happen. Let us do this analysis by product operators. As I said before, product operator has become so convenient, then actually do calculations in a very simple manner. So the product operator starting system is equilibrium situation. At time point one, the system is in equilibrium. Therefore, for a two-spin system, you have this Z magnetization as the equilibrium magnetization. So the operators for that is IKZ plus ILZ for the two spins. When you apply the first 90-degree pulse along the X, you get this density operator. This is minus IKY plus ILY as in the previous cases. During the next time period, which I will explain to you what all happens. During the next time period, T1 plus 2 tau, following evolutions will happen. We'll explicitly show the calculations for one spin, that is the K spin. The same thing will apply for the L spin as well. Chemical shift evolution will occur for the period T1 only, as they are refocused by the spin echo sequence during the period 2 tau. Okay, and the coupling evolution will happen for the entire period T1 plus 2 tau, because this is not refocused. Okay, so now what happens at now we want to calculate for one spin, that is the K spin. Let us say we have the KY operator there. The KY operator we are going to evolve IKY of this. Now first consider the chemical shift Hamiltonian, which will happen for the period T1, right? So chemical shift evolves for the period T1. So IKY, under the influence of the chemical shift Hamiltonian, that is the Zeeman Hamiltonian, it produces you IKY cosine omega k T1 minus IKX sine omega k T1. So now what we do is we make a simple abbreviation here. We write cosine omega k T1 is equal to CK inside bracket T1. Sine omega k T1 is SK T1. This is simply to reduce the writing. Okay, so abbreviation, make the whole thing look simpler. Okay, and then this cosine omega k T1, consider you have to evolve both these terms under the Hamiltonian now. The coupling Hamiltonian, right? But for how we do it, the coupling Hamiltonian is operative for the period T1 plus 2 tau. Okay, so therefore the Hj is operational for the period T1 plus 2 tau. So consider the first term here. This is the first term, that is this here. IKY cosine omega k T1 under the coupling Hamiltonian goes as CK T1, which is this thing here. IKY cosine pi JKL T1 plus 2 tau. Notice this we have put here not T1 but T1 plus 2 tau. Minus 2 IKX ILZ sine pi jkl t1 plus 2 tau. And that is written abbreviated form ck t1 inside bracket iky cosine pi jkl 1 plus 2 alpha t1. What I have done here is, for the period alpha, for the tau, I have put this alpha t1, which I gave in the previous slide. Tau is equal to alpha times t1, which is proportional to t1. Therefore, this becomes 1 plus 2 alpha t1 minus 2 ikx ilz sine pi jkl 1 plus 2 alpha into t1. Okay, so therefore now this becomes a factor which is multiplying the t1 with regard to the coupling constant. So now when you Fourier transform, the computer doesn't know that jkl is separate from this. You will consider the whole thing as coupling constant. jkl into 1 plus 2 alpha as the artificial coupling constant. That is what will happen when you do the Fourier transformation. It will appear that this is the entire coupling constant and is proportional to t1, is multiplied by t1. Okay. Similarly, ikx sine omega k t1 evolves under the coupling Hamiltonian as skt1, that is the second term. This is the second term what we are writing here. This ikx cosine pi jkl 1 plus 2 alpha t1, okay, and then plus 2 iky ilz sine pi jkl 1 plus 2 alpha t1. Therefore, put that together, the rho 3 is equal to ck t1 iky cosine pi jkl 1 plus 2 alpha t1 minus 2 ikx ilz sine pi jkl 1 plus 2 alpha t1 minus skt1 ikx cosine pi jkl 1 plus 2 alpha t1 plus 2 iky ilz sine pi jkl t1. Okay, now notice here we are not, there is no transfer, coherence transfer has not happened. This is only evolution under the Hamiltonian. Evolution under the Hamiltonian produces in phase and anti-phase terms, but it doesn't cause it a coherence transfer yet. Coherence transfer requires the 90-degree pulse. Huh? Okay, we have a blank here. Okay, let's go further. Thus, it can be seen that the coupling constant in the indirect dimension appears as 1 plus 2 alpha into jkl. So, that means the coupling constant appears scaled by a factor 1 plus 2 alpha along the f1 dimension in the 2D spectrum. Okay, so this is clear because it multiplies, j is replaced by j into 1 plus 2 alpha. Therefore, it will appear that the whole thing will appear as a coupling constant. So, it appears as scale. Now, in the above calculation, the T2 relaxation during the evolution period is not explicitly included. T2 relaxation would cause scaling of the line widths as well. Including the relaxation process, the rho 3 density operator will be like this. Now, okay, now let me go back to this blank slide here. So you had this pulse sequence. This was my pulse sequence. This is T1 and this is 1 plus 2 alpha T1 here. This is 2, this is tau and this is tau. Now, in the operator calculation, we did not include any relaxation. The relaxation does happen because the magnetization is in the transverse plane here. Okay, magnetization is precessing in the transverse plane and that will go through a T2 relaxation. T2 relaxation, how does that usually affect? So you have, let's say, an FID, it is decaying. The FID decays for two reasons. One thing is the recovering along the z-axis, other thing is the decay in the transverse plane because of the T2 relaxation. And this one you normally write as, let us say it is cosine part, cosine omega t into the e to the minus t by t2. So T2 is the transverse relaxation time. So 1 by T2 will appear as the line width. The line width, if I want to write, finally in the spectrum when you do it, it is proportional to 1 by T2. That is a factor, that is a time constant which will appear here. Therefore, whatever appears here in this exponential, this will show up as the line width. Okay. Now, during this pulse sequence, T2, okay, now normally when there is nothing else, it is actually T2 star because we have the inhomogenities, etc. all put together. That is the normal line width which will come. This is T2 star. T2 star includes the normal T2 relaxation plus due to the inhomogenities in your system. Now, where are the inhomogenities coming in this sequence? Now, you see there are two components of the pulse sequence here. During the T1 period, the full T2 star is operational. Here the T2 star is operational During the period tau 180 tau, there is a refocusing. There is a spin echo. The spin echo refocuses the chemical shift inhomogeneities as well. Okay. Therefore, during this period, the relaxation is operated by is determined by T2, not T2 star. Okay. So therefore, your total thing you will have to multiply by two components. So your normal f of t, okay, whatever it is, it should multiply by e to the minus t1 by t2 star multiply e to the minus 2 tau divided by t2. So this will be the factor which will multiply your ft without the relaxation period. Okay, that will actually determine your rho of 3. Whatever is rho of 3 which were calculated here without including the relaxation, that one will have to be multiplied by these two terms. The first one is because of the T2 star relaxation during the T1 period where the inhomogeneities are operational. During the tau 180 tau, during the spin echo sequence, T2 star is not operational because the inhomogeneities are refocused. It is only T2 which is operational. Therefore, it is a different number. Okay. So therefore, now the rho 3 star is the rho 3 multiplied by these two terms which I wrote just now. Rho 3 multiplied by e to the minus t1 by t2 star into e to the power minus t2 by 2 tau by t2. Okay, put that together in a simplified manner. So you get this is equal to rho 3 into exponential minus 1 plus 2 alpha t2 star by t2 into t1 by t2 star. Okay, so this is the multiplicative factor that has come because we have differential relaxation rates during the two segments of the pulse sequence. So essentially what I've done is simply put these two together. So this is you take out T1 by T2 star, then you get the T2 star by T2 here. For the 2 tau, we have put here 2 alpha. That's it. Okay. So you get this. So therefore this becomes a multiplicative factor. So that is you write it in this manner. So you have rho 3 star is equal to rho 3 into e to the minus beta T1 by T2 star. In the absence of this, what would have normally written? Rho 3 is e to the minus T1 by T2 star. That's the usual thing which 1 by T2 star determines the line weight. Now you have a factor beta which is also contributing to the line weight. Because when you do Fourier transformation, this will appear as though minus beta by T2 star is appearing as a line weight. Okay, where beta is equal to 1 plus 2 alpha T2 star by T2. Now, 1 by T2 star represents the normal line width. It is seen that this pulse sequence, the line width along the F1 dimension will be scaled by a factor beta. 1 by T2 star multiplied by beta. That's what it is, scaling factor there. So you scale the coupling constants by the factor 1 plus 2 alpha. You also scale the coupling scale the line weight by a factor beta. Now the question is, when do we get the benefit? Okay, in the event T2 star is equal to T2, the line width scaling factor will be identical to the J scaling factor 1 plus 2 alpha. Suppose T2 star is equal to T2. You have absolutely no inhomogeneities at all, and you are perfectly well-shimmed magnet, and there is no inhomogeneity absolutely, then T2 star will become equal to T2. In that situation, J scaling does not necessarily increase the resolution in the fine structure because you are increasing the separation, but you are also increasing the line width. Therefore, how does it help? Okay, therefore, then it does not help. However, most of the times, this condition is not satisfied. You can never achieve a situation where T2 star is equal to T2. It is almost never possible. Therefore, J scaling helps to improve the resolution within the fine structure. So therefore, the benefit of this J scaling along the F1 dimension is to increase the separation between positive and negative signals in the Cauchy spectrum and thus lead to reduction in cancellation of intensities. In other words, it increases the sensitivity in the cross peaks and it also allows you to measure the coupling constants in a more accurate manner. Just here is an experimental example. Experimental J is a very simple molecule which you have taken here. This is uracil. Uracil has just two protons. Okay, these two protons H5 and H6 here. So therefore, it is a simple two-spin system, and you have the diagonal peaks here and the cross peaks here. Okay. Of course, when you scale it along F1 dimension, this scaling will appear both in the diagonal as well as in the cross peaks. As you have seen, 1 plus 2 alpha factor appears everywhere. Now, you just take the blow up of this. Here you see this actual coupling constant which is along the F2 dimension. F2 dimension, what you measure is 7.6 Hertz. Of course, here the resolution is already very good. So therefore, this is a small molecule, there is no issue there. And when you measure along the F1 dimension, it is 4 times scale. Okay, so you can see the separation is so very well seen. So it is 30.4 Hertz. That is the separation you have along this. This tells you that the experiment is working, and it is not that you are losing any information because of the change in the line width. That does not happen. Therefore, you are getting a good scaling here, and you can measure the coupling constant more precisely. In a situation, we would like to measure the coupling constant along the F1 dimension and divide by the scaling factor to get the accurate value of the coupling constant. Suppose you are not able to measure this one very well. Okay, this separation you are measuring in some way, you get some number, and you measure this separation in along the F1 dimension. If these things don't match, then I will say I will take the F1 dimension separation. Because the F2 dimension, the cancellations might have happened, some partial cancellation, as a result of which the peak centers could have shifted. Therefore, you may measure a wrong coupling constant. But you measure along the F1 dimension, then you will get a pretty accurate value of the coupling constant. Okay, now the same pulse sequence, we make another trick. We make it slightly different so that we can actually scale the chemical shifts now, not the coupling constants. We scale the chemical shifts. How do we do? The pulse sequence remains the same. The shifts case, but only the trick of adjusting the delays. How do you adjust the delays? You see here, what we have done here is the 90, 180 tau. So in this period, what was T1 earlier, we have made it as 1 minus alpha times T1. And this whole period from here to here is T1. In the previous case, what was it? From here to here, it is 1 plus 2 alpha T1. Okay, T1 was increased. T1 was increased by the factor 2 alpha. Therefore, in this situation, we make the distance from here to here as T1. We keep that constant. Okay, and now this period is the same again, tau tau, and 2 tau is equal to alpha T1. Okay, this period from here to here is alpha T1, and therefore, what is this separation? This will be 1 minus alpha times T1. The evolutions will happen in the same manner as before, except now the chemical shifts will evolve for the period 1 minus alpha times T1, not for the period T1. Chemical shifts will now evolve for the period 1 minus alpha times T1, whereas the coupling constant will evolve for the whole period T1. Okay, so what will happen then? Choosing your value of alpha, since alpha is positive, your chemical shifts will be scaled down. Chemical shift will come down because 1 minus alpha is all, of course, less than 1. Therefore, it will appear as though the chemical shifts are scaled down. The separation between the peaks is decreased, not in the fine structure. The fine structure remains the same because there is a T1 here. The T1 remains the same as the coupling constant evolves for the whole period T1. Okay, therefore, coupling constant remains the same, but the chemical shift appears scaled down by 1 factor 1 minus alpha. Okay, so let's see how this happens. Same way, already IKZ IL plus ILZ rho 1 and rho 2 is minus IKY plus ILY as before. During the time period of T1, following evolutions will happen. Okay, chemical shift will occur for the period 1 minus alpha times T1 only, as they are refocused by the Spinnaker sequence, while J coupling evolution will happen for the entire period T1. Okay, so okay, let's go up there. So in this case, therefore, evolution under Hamiltonian gives me IKY cosine omega k 1 minus alpha times T1 minus IKX sine omega k 1 minus alpha times T1. Okay, now you consider both the terms under the J coupling. IKY cosine omega k 1 minus alpha times T1 under the influence of the coupling Hamiltonian. I take out this factor, this is the coefficient. Inside you right now, IKY cosine pi jkl T1. Notice, this is the difference here. Earlier we had 1 plus 2 alpha T1. Now this will be simply T1. And that factor has been now brought into the chemical shift. Pi jkl T1 minus 2 IKX ILZ sine pi jkl T1. And the second term, IKX sine omega k 1 minus alpha times t1 is under the coupling Hamiltonian will be ikx cosine pi j k l t1 plus 2 iky ilz sine pi j k l t1. Thus, rho 3 is now cosine omega k 1 minus alpha times t1 inside bracket iky cosine pi j k l t1 minus 2 ikx ilz sine pi j k l t1, and the second term minus sine omega k 1 minus alpha times t1 inside bracket ikx cosine pi j k l t1 plus 2 iky ilz sine pi j k l t1. So it's clear now. What is the result of this? When you Fourier transform it, you will get the chemical shifts as omega k into 1 minus alpha and the coupling constant as jkl. So therefore, thus the chemical shift appears downscaled by a factor 1 minus alpha along the F1 dimension. This enables improving the resolution in the multiplex structure along the F1 dimension by increasing the T1 max. Okay, how does this happen? Let me go back to the blank slide here. So when you are actually doing your FID is here, you are collecting data points like this, right? And same thing happens in the T1 increments also. You collect T1 points one by one. Here you collect the T2 points one by one here. What is the separation between the points? Separation between the points, if your maximum frequency is omega max, let us say, then that is called the dwell time, right? The sampling frequency is, so your dwell time is 1 by 2 times omega max. Okay. So omega max is the maximum frequency in your spectrum. Now, the dwell time determines what will be the total time you collect, the FID number 1. And if you collect the FID for longer period, total acquisition time, if acquisition time is AQ, let us say, then your resolution is proportional to 1 by AQ. Intrinsic resolution in your spectrum is proportional to 1 by acquisition time. So the longer you collect the data, higher will be the resolution in your spectrum. How we can do it? There are two ways you can do it. One is to increase the separation between the points, or you collect more points. Collecting more points is easy in the T2 dimension, but collecting more points in the T1 dimension is not easy. You'll have to collect more and more. That will mean more machine time. So what you can do is you increase the separation between the points. If I increase the separation between the points, I have to reduce the spectral width, right? The omega max will have to be reduced. That means I have to scale down the chemical shifts. If I scale down the chemical shifts uniformly, then the omega max is smaller. Therefore, the dW increases. Say for the same number of T1 increments, I will have a higher acquisition time. So this will result in better resolution in your spectrum. Okay, so that is what explained here. Okay, so therefore, by increasing the T1 max for the given number of T1 increments, we will get a better resolution. Okay, now what about the line width? Of course, can we afford it all the time? Can we afford this? If we reduce the separation between the peaks, of course they can merge also. You have to take care of that. How much you want to scale it down? Alpha is your choice, whether you can make it 0.5, 0.6, 0.7, 0.8. Of course, it has to be less than 1. That is, you can choose that. To whatever extent you can afford it, you can choose the value of alpha. Now, what about the line width? The line width also will get changed when you do this. So in the above calculation, T2 relaxation during the evolution period is not explicitly included. So T2 relaxation would cause the scaling of the line widths as well. It is exactly in the same manner as I explained to you earlier. So now the rho 3 density operator can be written as rho 3 star is equal to rho 3 e to the minus T1 by T2 star inside bracket 1 minus alpha. This is where the chemical shift evolution is happening, plus alpha T2 star by T2. This is where the coupling constant is happening. Coupling evolution is happening for the whole period. So if you look at this, they separate it into 2, e to the minus T1 by T2 star into 1 minus alpha. And the second portion is giving me simply e to the minus alpha T1. Because T2 star will cancel here, e to the minus T1 by T2. Alpha T1 by T2. No, yes, alpha T1 by T2. T2 star and T2 star will cancel. So e to the minus T1 by T2 star. So okay, now here is alpha. Chemical shift is evolving for 1 minus alpha and the coupling constant will evolve for minus T2. Okay, now again, there is a mistake here. Yes, alpha should not be there here. So minus T1 by T2 star into T2 star by T2. So T2 star will cancel. So you will get T to the minus T1 by T2. So that is the coupling constant evolution. 1 minus alpha is the chemical shift evolution. Therefore, we get minus T1 by T2 star there. So therefore, now this also will go. So that's clearly the line weights are scaled by the factor 1 minus alpha plus T2 star by T2. Okay, minus T1 by T2, that is correct. Okay, so in the event T2 star is equal to T2, the line widths will not get scaled. What happens? T2 star is equal to T2, this will go away. Hey, hold on, it should become, in the T2 star is equal to T2, the line widths will not get scaled. If T2 star, so this will become equal to 1. Minus alpha plus alpha, it will become alpha. 1 minus alpha plus alpha. So this will become simply minus alpha. No, this should be there. Okay, fine, sorry. Okay, so therefore in the T2 star is equal to the line widths will not get scaled. If T2 star is less than T2, as it happens in most practical cases, line widths will be scaled down. Okay, this factor will be less than 1. Therefore, this 1 minus alpha plus T2, this will actually reduce the scaling factor. Okay, so this is less than 1, and therefore this whole thing will be, this will result in better resolution in the multiplex fine structure. So let us look at this one more if there is any mistake here. Sorry. So what happens if it is T2 star is equal to T2? So this will cancel. There is 1 minus alpha plus alpha, therefore it goes, and therefore minus T1 by T2 star. So somebody was entering. Okay, so then it will be minus T1 by T2, and therefore there is no scaling. There is no benefit. If T2 star is less than T2, this factor will be less than 1, and alpha is also less than 1. Therefore, this is alpha will, this whole thing will not cancel. 1 minus alpha plus this factor which is less than alpha. Therefore, this factor will be still less. Therefore, line widths will be scaled down. Therefore, instead of minus T1 by T2 star, minus T1 by T2, it will be a factor which is some multiplicative factor which is less than 1. Therefore, this will result in better resolution in the multiplier function. Okay, this is correct. Okay. So therefore, in the event T2 star is less than T2, as it happens in the most practical cases, the line widths will be scaled down, and this will result in better resolution in the multiplex fine structure. Okay. So therefore, now you see the experimental example here. See this fine structure. The fine structure is much better obtained in this all these peaks. This is a spectrum for the nucleic acids. This is a nucleic acid spectrum taken from proteins and nucleic acids. So, and the fine structure is much better seen here. Why it is seen better? Because we are able to increase the T1 max for the same number of T1 increments. Because scale down the chemical shifts by a factor of half here. And so you can afford it because the peaks are quite well separated. Therefore, you can always afford to reduce this separation between them and increase the multiplet resolution in the spectrum. Okay, so therefore, this helps in the experiment shift scale Cozy experiment. Okay, all right. So now we turn to another kind of an experiment which is called total correlation spectroscopy. This is a different concept now. This is a different concept now. The pulse sequence is, first let me explain the pulse sequence, and then afterwards we will do the analysis of this. Well, here the analysis is calculation is more complicated. We will take the results there. Okay, the simple product operator description which we gave is not sufficient here because of the strong coupling. Okay, first of all, what it contains? It contains a 90-degree pulse. Then you have the T1 period. Then you have got the spin lock, and then the due to detection as T2. Now, what is a spin lock? This is important to understand. What is a spin lock? Okay, now let me go to a blank slide. There is a blank slide. Okay, so now what is a spin lock? In the normal situation, when your magnetic field is along the z-axis, magnetic field is along the z-axis. Your magnetization is along the z-axis, right? This is your magnetization. It is along the z-axis. So then I can say there is nothing in the transverse plane. At equilibrium, there is nothing in the transverse plane. So I can say the magnetization is locked along the z-axis. In this situation, there is no other magnetization. It is only along the z-axis. It is locked along the z-axis. Now what I want to do is, I want to lock the magnetization in the transverse plane. I want to do it in the transverse plane, along the x-axis or the y-axis. So how do I do it? So what I do, first I apply 90-degree pulse. When I apply 90-degree pulse, the magnetization comes in the transverse plane here. Okay, and all the magnetization has been rotated here. Now I apply, and this is of course they have different frequencies. When I remove the pulse, they will all start processing the T1 period. They will get frequency label. During that period, they will get frequency label. Now what I do is apply a second RF along this axis. We call it as B2. Let us say we call it a B2 along this axis. So in this one, which is the field available? The only field available is the B2. There is no field along the z-axis because we are in the rotating frame. When you magnetization is rotated into the transverse plane, then we are sitting in the rotating frame. In this rotating frame, there is no field along the z-axis. Essentially, like applying the pulse also. In the application of the pulse also, you did the same thing. The your field was along the z-axis, and you applied the RF along this axis here. This was the B1 field. The B1 field was sufficiently strong so that the entire magnetization would actually tend to align itself with respect to the B1 field, because if it is much stronger than the field in the rotating frame, is omega I minus omega naught. Individual frequencies omega I minus omega naught. This is the frequency. You convert that into the divided by the gyromagnetic ratio. This will give you the field in the rotating frame. This is the field in the rotating frame. Okay. Now if omega I is equal to omega naught, then this field along the z-axis will be 0. This field, okay, B0. Okay, now let me call. This is B0. Okay, this is the normal field applied. This is the field in the rotating frame. This will be 0 when you are on resonance. Now, can you be resonance for all of them? You will not be on resonance all of them. What happens is you will have the HI here and you have the H1 here. Okay, now this is the, sorry, I keep messing up with B1 and H1 and things like that. Okay, this is B1 here, and this is your rotating frame field, and this is my H1. So your effective field will be here, right? So if H1 is far, far larger than HIR, for all values of I, for all I's, then what will happen? The effective field will be along this H1, right? So therefore, that means the only field which is available is along the H1 dimension, and that is called as the locking. So you have the effective field along the transverse plane. Therefore, what will happen to the spins? The spins will tend to align themselves with respect to this field, not the H0 field. In the absence of anything perturbation, the spins are locked along the z-axis. Now, I artificially create a situation in the rotating frame that you have all the spins aligned along the H1 or along the B1 or the B2, whatever you want. So you call it B2, you may call it B2. Here for the pulse, application of the pulse, we call it as B1 or H1. So, and now apply it, after the pulse is applied, I apply this B2 in the transverse plane. And this is a very powerful, strong field. Of course, not like the B0, but in the rotating frame, you don't need to apply such a strong, because with the frequency, you are going to the frequency and you're eliminating the frequencies there. Therefore, this B2 field is applied in such a way that the spins are locked along this axis. Here, you may think that, okay, they're processing around this. Okay, so they will be locked along the B2 axis. This is called as a spin lock. The magnetization stays there. Okay, everything, no matter what you have processed, then when the spin lock is on, they will all get locked along that particular axis. If the B2 is applied along the y-axis, they will be locked along the y-axis. If you apply it along the x-axis, you will apply it on the x-axis and so on. Wherever you apply it, it will apply there. No, then of course you may also ask, what is the meaning of applying a pulse along the x or the y-axis in the transverse plane? What is the physical meaning? This is basically a phase relationship. It is a phase relationship between the RF and your receiver. You take the receiver as 0 phase, and whatever is we call that as the x-axis or the y-axis, whatever receiver phase. Phase difference between the receiver and your RF, that is what is called as the phase. That is, if that is along the y, this is along the x, and so on and so forth. It's basically the phase difference between the receiver phase and your RF phase. So that is in common language, you call it as along the x-axis or the y-axis. If the phase difference is 45 degrees, then it is somewhere in between between the x and the y-axis. So that is the nomenclature which is used. So once you do that, okay, then your magnetization is locked. That is the magnetization is locked along the z-axis, along in the transverse plane. Now, what is the consequence of this? If the spins are locked along if there is no chemical shift, okay, if there is no chemical, if the spins are locked along one axis, there is no chemical shift. Chemical shift evolution is not there. Only interaction with that small field, the B2 field of course will be there, but that field is so small compared to this B0 field, you can almost ignore that. You can almost ignore it. The interaction between the spins K and L becomes much stronger than that particular interaction. But this is a much larger interaction there. Therefore, we can no longer approximate your coupling Hamiltonian as only 2 IKZ ILZ. This will become a strong coupled situation, strongly coupled situation. During the spin lock, the effective Hamiltonian will be only the coupling Hamiltonian. The chemical shifts are eliminated because we are locked the spins along the z-axis and there is no precession over there. They are all locked there. Okay. Therefore, the effective Hamiltonian is Ik dot IL. Of course, the J coupling constant is there. Now, therefore, if it is Ik dot IL, we have to consider all the three. IKZ, ILZ, IKX, ILX, IKY, ILY. When you are actually, you must have done this already in the analysis of the spectra. Analysis of the spectra of two spins. Okay, weakly coupled situation versus strongly coupled situation. When you do the strongly coupled situation, you will have to consider all of these terms in your Hamiltonian. For the calculation of the energies, calculation of the transition frequencies, for all of that you need to consider all of this. When it is weakly coupled situation, your Hamiltonian is only this. Now, the product operator, which we have discussed, is applicable only when your coupling is weak. For this situation, it is not applicable. Some special tricks have to be made. This has been done. Of course, we don't have the possibility of going through that one here now. Therefore, we will only take the result of that calculation, what comes as the result of calculation of the evolution under this Hamiltonian. And those of you who want to know more about it, of course, can look at the book by Richard Ernst and a couple of other people, where the details of these calculations are given. In the original papers in JMR, also this is given. They make certain combinations of this and develop new formalism over there to treat this strongly coupled situation. Okay, but we will take the result which is important for us. Okay, now what is the effect, what is the result of this? I start with, let us say, IKX operator, because after the 90-degree pulse, the two spins are still independent, IKX and ILX. They are independent, right? Now, one more thing I must tell you with regard to when it is a strongly coupled situation, the spins lose their identity. Why do they lose their identity? Because their chemical shifts are gone. You separate the spins on the basis of the chemical shifts. But if the chemical shifts are gone, the spin identity is lost. Therefore, we say in the strongly coupled situation or in the spin lock, the spins lose their identity. But during the T1 evolution period, spin lock is not there. Therefore, individual spins K and L are still there. We can talk in terms of the evolution of the spins during the period T1. So they do evolve. After that, then you have to apply the strongly coupled Hamiltonian to consider what happens to the terms as they evolve. Okay, so this is the way it will come. IKX under the influence of the Hamiltonian HE for the period T gives you IKX inside bracket 1 plus cosine 2 pi j t divided by 2 plus ILX 1 minus cosine 2 pi j t divided by 2. Plus IKY ILZ minus ILY IKZ sine 2 pi j_t. Notice here, the spin lock has already caused a coherence transfer. In the Cauchy case, we have applied the 90-degree pulse to cause coherence transfer. Here in the transverse plane, in the rotating frame, the spin lock which is there on the transverse plane actually causes a coherence transfer already. Okay. Now this one, which is the Kx term, which will give you a diagonal peak, and the ILX term gives you the cross peak. And these are two antiphase terms which will actually be eliminated. They will decay and they will be eliminated. Okay. So now, another thing what you can see here is Kx is giving to Kx and Lx. In the Cauchy spectra, what we got? Kx, and Ly. We got Ly here, right? In the double quantum filtered Cauchy, of course, we got Kx, and Lx, Kz. So therefore, the phases were the same, XX here. So here it is, but in double quantum filtered Cauchy, it was antiphase, Kx, Lz, and Lx, Kz. So 2 Lx, that is what it is. Here we are getting in phase transfer. Ikx giving you Ikx and Ilx. So these are in phase terms. Okay. And these are multiplied by this coefficients here, 1 plus cosine 2 pi j t, 1 minus cosine 2 pi j t. And what is t here? T is not the t1. T is not t1 here. T is the period for which you apply the spin lock. This is the transfer happening during the spin lock. After the evolution in T1, you applied the spin lock for a period T, okay? And that is approximately of this type. Now, if T is equal to 1 by 2j, consider situation. If T is equal to 1 by 2j, what happens? This T 1 by 2j, this gives you cosine pi, okay? Cosine pi is minus 1. Therefore, the first term will go to 0. And the second term will become 1 plus 1. But then it becomes 1 minus of minus 1. Therefore, it is 1 plus 1. Therefore, it becomes ILX. Okay. So, and the second term here is 1 by 2j sine pi. This will go to 0. Okay. So, this will go to 0. Therefore, so diagonal will go to 0 in this. So the diagonal will go in 1 by 2j. If t is equal to 1 by 2j, diagonal will go to 0, cross will go to 1. So complete transfer. If you put t is equal to 1 by 2j, there is a complete transfer of magnetization from K spin to L spin. Now, you remember the inept. In the inept also we could transfer coherence, right? In the refocused inept, when we did refocused inept, there was a complete transfer. It went from one spin to another spin. And but how much time it took there? It took 1 by j. The first 1 by 2j was to create antiphase magnetization in the inept. And at that time, antiphase magnetization means they were their opposite signs. So we cannot decouple there. In order to decouple, to be able to decouple, you put another 1 by 2j, therefore it becomes 1 by j, and the total transfer then will occur only for 1 by j, to pass a period of 1 by j. And this you have achieved almost twice, half the time, achieved in half the time. And a second important thing is, both the diagonal and the cross peaks have the same phase. What do you mean same phase? They are both x and x here. Suppose I started with y, I will get ky and ly. Notice here, of course, we are not doing a calculation with kz, lz, but in principle, it is also applicable to kz, lz. So, but by and large, we in the rotating frame, when we are talking about, we do kx, lz. You can involve the kz operator under the influence of the spin lock Hamiltonian. That is perfectly fine. That one can do that also. But we don't want to consider that here now, simply because we are in the transverse plane, magnetization in the transverse plane. Therefore, we treat the kx and the ky terms only. So the ky goes to ky and ly, kx goes to kx and lx. Therefore, in phase transfer, in a much shorter period, you get much better transfer of magnetization from the spins. So what is it? And then this, of course, goes to 0 when you put 1 over 2, 0. Now, what is the typical value of J? Now, can we always optimize this? J can vary. In the homonuclear situations, J can vary from 3 hertz to 10 hertz and things like that. So, or even more. So, obviously, you cannot be choosing a one particular value of J for all which will suit all of them. So, typically, you have to see where you want to maximize your transfers. One can optimize the value of things there. And remember, during this spin lock period, there will also be relaxation. The relaxation is the transverse relaxation. The transverse relaxation will happen during the spin lock period. And transverse relaxation is faster than the longitudinal relaxation. Therefore, you have to optimize on the relaxation, optimize on the spin lock period versus the coupling constant versus the variations in the coupling constant and so forth. So this is something by trial and error one can get for the different kinds of situation. Okay. So now you see, I wrote the same thing here. Earlier I said for a vertical ULFG. Now you write the same equation for ILX. I wrote the ILX equation for the IKX earlier, right? Now write the same equation for ILX. So what will happen now? I will transfer from ILX to IKX. The ILX gives me ILX 1 plus cosine 2 pi jt divided by 2 plus IKX 1 minus cosine 2 pi jt divided by 2 plus ILY IKZ minus IKY ILZ sine pi jklt. Now, both the spins are experiencing the spin lock at the same time. Okay. Therefore, in both cases, the transfer is happening. Now, we add these two. You see, this furrow will get cancelled out. So, therefore, in order to cancel this, you don't need to worry about this J coupling constant there. That will automatically get cancelled out when you have two spins like this. The transfer is happening at the same time in both the spins. Therefore, IKX plus ILX goes to IKX plus ILX during this period. So, in phase transfer, this is the most important thing. This implies that the total X magnetization is conserved through the mixing sequence, and there is in phase transfer IKX to ILX and vice versa, retaining the phase of the magnetization. IKX goes to ILX, IKY goes to ILY, and IKZ goes to IZ. Because IKZ goes to, you can do the calculation IKZ, ILZ also. But for the transverse plane, we are not concerned about that. Therefore, the mixing is termed as isotropic mixing. Because you maintain this X and X, Y and Z, this doesn't the phase, does not change the phase of the individual magnetizations. Therefore, this mixing is called as isotropic mixing. Whatever mixing happens during the spin lock is called as isotropic mixing. And the Hamiltonian is therefore termed as isotropic Hamiltonian. The strongly coupled Hamiltonian here is now termed as the isotropic Hamiltonian. After the mixing, the magnetization components are detected in the T2 time period. A two-dimensional Fourier transformation of the collected signal results in the 2D spectrum as usual. Okay. Now you see here, because of the in-phase isotropic mixing, relay of magnetization can happen through the coupling network. You see, you don't need an antiphase magnetization to cause a transfer magnetization. You transfer the IKX to ILX. Okay, this is an in-phase transfer. Now, there is no coupling between K and M, but there is a coupling from L and M. Now, since all the spins are locked at the same time, what prevents the magnetization going from L to M? You cannot prevent that. So, at the same time, therefore, there will be relay of magnetization through the coupling network. In a coupling network, if a transfer happens from K to L, it can also happen from L to M. So therefore, it can, whatever has gone from K to L can further get relayed to M. Right? So therefore, in a coupling network KLM, transfer can occur IKX, ILX, IMX. And therefore, you get a complete network of couplings in the Coxey spectrum, which you don't get in the Cozy spectrum. In the Cozy spectrum, you'll only see the directly coupled spins. Uncoupled spins, you don't have a cross peak. Here, you will have a cross peak in entire coupling network. That is the power of the Coxey experiment. It produces so much more information in your spectrum, and you can see that here already. So here is a particular example. So you have this is a complex spectrum on the top. In the Cozy, you have this relate to this and to this. There are two peaks appearing there. Now in the Coxey, you have from the same one, you have this which is the same as that, and then you have one of them here. That is this here, but you see so many others. So because there is a network of couplings. Because of the network of couplings, it gets relayed all through. So you can, if you analyze all of this, you can figure out what is the nature of the coupling network in your molecule. Okay, so therefore you see so many peaks. You see this horizontal one here at the end. This is the same thing what I shown there. So this one has a coupling here in the cozy. Now this fellow shows here to here to here, here. So many. So many protons are coupled. Is the relay. Not that there is a coupling between each one of them, but there is the relay. K to L, L to M, M to P, P to Q, Q to R, and so on and so forth. Because each of these coupling constant can be large. Okay. Of course, the total intensity gets distributed over there. That is okay. But you have the information. You can signal average more. You have the full information about the entire coupling network. So this is particularly important from the analysis of the spin coupling networks in the spectrum. Should we take a break?
Yes.
Huh?
Yes, yes.
So,
So this in toxin,
yeah.
So is there any phase this CBC? If you see the cross peaks, so they have different.
There is some noise. There is some noise, but the phases are all the same. There is some noise over there. I'm sorry.
Okay.
There is some noise over there. See, the intensity gets distributed over all of.
That's why the noise.
That's why the noise comes up. Yeah.
And so again, this one more thing. Go to here slide.
Yeah. Here?
No. I see. You can see here. So this coefficient of IKX.
Yeah.
Is 1 minus cos 2 pi. So why this in the first case now ILX it is plus, but that IKX
That is a transfer peak, no?
Okay.
That is a cross peak.
Okay.
So here this is diagonal.
Okay.
This is the cross. For the cross peak, it is always 1 minus. In the previous also, it was like that. Yeah. Okay, so we'll take a 10 minutes break here.
So I think you are still in this.
Yeah, I'm still in the 13. How many are there in this? Still more?
Sure. How many slides are there?
There will be still maybe 7, 8.
Another 10.
Okay, doesn't matter. I think it's okay.
38. So we have. So
No, but there are some blanks also.
Yeah. 6 around. 6 5 to 6. Hey, around 10. 10. Around 10 slides.
I think it's okay, but it is important. Those are important concepts which have to be given. Which that's why I put blank slides and then try to explain that. Otherwise, if the spin lock is not clear, you cannot go forward. In the rosy also the spin lock comes in, but that is a slightly lighter power.
You can go to the participants if they
have any questions
at this stage. They can ask. Just unmute them. They are muted. Just write one line. Any question at this stage? Any question, and then you write that you join thereafter. Any questions? Question marks there. We'll join after 5 minutes. Right.
You have to start after 5 minutes.
Ask.
How many are there? Are there 7, 8? How many are there?
Yes, sir.
8. 8 are there. Okay. So now we are entering a new set of experiments, which is fundamentally different mechanism of interaction. So far, we are considering all J-dependent experiments, COSY, double quantum filtered COSY, or whatever we discussed. All of them were dependent on the J coupling for transfer of information from one spin to another information. Now we turn to the other kind of interaction, which is based on the dipolar coupling between the spins. This happens through space. Two-dimensional nuclear Overhauser effect spectroscopy. We have discussed the nuclear Overhauser effect earlier, and that was dependent on the NOEs. The NOE is dependent on the dipolar coupling. Therefore, we want to convert that one-dimensional experiment into a two-dimensional version. The transient NOE is what is basically a one-dimensional NOESY experiment, so to say. So here we are doing a two-dimensional version of that, and the pulse sequence is indicated here. This is again a very simple experiment. This is fortunately one experiment which can actually explain by hand waving, sort of. You can use the vector pictures and see what is happening here. Although one can do a detailed quantitative calculations using the density operator, which we already indicated how to calculate using Solomon equations, how to calculate rigorously the intensities of the peaks, NOEs and things like that. The pulse sequence simply has 3 pulses, 90, T1, 90, tau m, 90. So these are 3 pulses here. Now notice here again, I have put here phi and phi. Phases, for the first 2 pulses, I put the phase phi. And remember, this was the same which was used in the double quantum filtered COSY. Okay. And the double quantum filtered COSY, we kept those phases and we had a particular way of choosing density operators, certain portions of the density operator. If you remember, we had after the T1 evolution period, we had the terms which contained, if I started from IKZ, IKX, I had the terms going to IKZ and to IKY, ILZ, and IKX, and to IKZ, ILX, kind of a thing. And we converted them into we eliminated this. We said we will not use this. Okay, so the IKY, ILF, okay. I've written a short form there. IKX, ILZ, and to IKY, ILZ. And thus I had this here, the IKY. Let me write it again. This was the COSY part. This was the COSY part. IKX, IKY, ILZ, and IKY, IKX, ILZ. This was after the evolution under the coupling constant. We had these 4 terms, and we eliminated this part to get the COSY spectrum. In the double quantum filtered COSY, we eliminated something else. We eliminated all the single quantums, we converted this into double quantum. One of the terms is a double quantum, and chose that. Now what we want to do is, this will get converted into, what will get this converted into? After this evolution, this will get converted into IKZ here, and IKY, ILX, sort of the double quantum one, and this will be IKY, IKX, ILZ. This will remain like that only. Okay, and we chose this, and in the double quantum filtered COSY, we chose this part. In the COSY, we chose this part. Okay. ILX. In the COSY, we chose this one. In double quantum filtered COSY, we chose this one. Now we want to choose this. We want to choose IKZ. Okay. This is done by the same sort of a phase cycling what I indicated there. In the kind of a double quantum filtered COSY, the phase phi was run in the same manner, x, y, minus x, minus y. Okay, in double quantum filtered COSY, we had x, y, minus x, minus y, set of 4 experiments, but the receiver was plus, minus in the double quantum filtered COSY. Now we are doing the phi phase also goes same way, x, y, minus x, minus y, but receiver phase does not change. We all add plus. As a consequence of this, we will only pick up this term, and eliminate all the others. So therefore, at the end of this here, I will have only IKZ. Okay, let's see if there is this indicated in the slide. Do I have the product operator there? Yes, it is there. Product operator. Okay, before we go to the product operators, I explained to you the philosophy there, but we will see that explicitly in the product operator. Okay, so this is the philosophy is this: at this point, at the point 4, I will have only ikz. I start from ikz here, and I will have only ikz at point 4. Okay, how it comes? The exact calculation I will show you. But during this period, tau m, what happens during this period? Tau m, there is a transfer of magnetization from K spin to another spin which is close by in space. Let's say that is a L spin. Okay, certain portion of that gets transferred to the L spin. Let that factor be Q, and other things remains with the P itself. So we will have here components QLZ and P KZ, IKZ. So we have both the components present here at this point. Therefore, when I measure it, 90-degree X pulse, and then I start measuring it, I get the components from here and here. Therefore, there is a relay of information from K to L through dipolar interaction, and that depends on the mixing time here, how much time you give for this transfer to happen. This is the dipolar relaxation mediated transfer, and therefore this will depend upon how much is the mixing time. And actual calculation of mixing time dependence, we have already shown that when we discussed the NOE in a rigorous manner earlier. Okay, so now we will see the product operator calculation of this. What I explained to you earlier, I'm just showing you by the calculation how we are picking up only those particular terms. I wrote, okay, rho 4 phi is equal to x. This is what is rho 4? Rho 4 is the density operator after the second 90-degree pulse. If phi is equal to x, we get minus ikz cosine pi jkl t1 minus 2 ikx ily sin pi jkl t1 cosine omega k t1 plus ikx cosine pi jkl t1 minus 2 ikz ily sin pi jkl t1 sin omega k t1. If rho 4 phi is equal to y, I repeat the calculation keeping phi is equal to y, then I will get again minus ikz cosine pi jkl t1 2 iky ilx. Notice the difference here. Here was 2 ikx ily. I get here 2 iky ilx. Sin pi jkl t1 cosine omega k t1 plus iky. Notice here I had ikx. Now I have iky. Iky cosine pi jkl t1 plus 2 ikz ilx. Sin pi jkl t1 sin omega k t1. Now if rho 4 phi is equal to minus x, so essentially it will be similar to this but with the small changes in the sign. That will be minus ikz cosine pi jkl t1 as here, and minus 2 ikx ily as here, sin pi jkl t1 cosine omega k t1. And this part will be minus ikx cosine pi jkl t1 plus 2 ikz ily, because I changed the phase of the phi of the pulse, plus 2 ikz ily sin pi jkl t1 sin omega k t1. Now rho 4 phi is equal to minus phi, again similar to this but with a small change in the signs. So you get first term is the same, minus ikz cosine pi jkl t1 plus 2 iky ilx sin pi jkl t1 cosine omega k t1 minus iky cosine pi jkl t1. Notice the change in sign here, this and this, minus 2 ikz ilx, again notice the sign change here, minus 2 ikz ilx sin pi jkl t1 sin omega k t1. Now what I am doing is I am simply adding all of these. When I add all of these, what will happen? This will cancel with this, this will cancel with this, this will cancel with this. Okay, and then similarly, the thing which only remains is the ikz. That has not changed at all. Okay, so this will cancel with this will cancel with this. Oops. So therefore, when I add all of something else. Which में क्या है? Something in here. Okay. So now if add of all of this, what I get is minus 4 ikz cosine pi jkl t1 plus 2 iky ilx minus 2 ikx ily sine pi j k L T1 cosine omega k T1. We get ikz plus we also retain this part. This also remains. This did not cancel. IKY ILX minus 2 IKX ILY. This did not cancel. This remained. And what is this? This is pure zero quantum coherence. This is Z magnetization and this is pure zero quantum coherence. Yet it is the sine pi j k L T1. Now this, remember, this is the zero quantum coherence. The zero quantum coherence, during the mixing time, what happens? It decays. The kz is along the z axis. The kz is along that is therefore determined by the T1 relaxation time. Z magnetization reverses towards the equilibrium value of the K spin along the z axis dictated by the T1 relaxation time. The zero quantum coherence decays due to T2 relaxation time. Okay. The residual, no, sometimes suppose something does not decay. Okay. All of it has not gone. So what will happen then? So we'll have a problem because we'll start getting mixed up with this. The phase mixing will happen with this. We have to eliminate this. We have to remove the zero quantum coherence. The zero quantum coherence cannot be removed by phase cycling because the theory of phase cycling, see, if you make a phase change, it is multiplied by what is called the coherence order, and the coherence order for zero quantum is 0. Therefore, phase cycling has no effect on the zero quantum coherence. Therefore, this will remain. And the residual zero quantum, in order to remove that, what we have to do is we have to allow it to evolve for different periods of time. It will evolve under the influence of the relaxation, right? It will evolve because of the coherence, and it will acquire different phases depending upon the time for which it evolves. Now, during the time tau m, it is evolving. Zero quantum coherence is evolving. Okay, so therefore it acquires a certain phase. Zero quantum coherence will acquire a phase. Now, if I want to cancel this, what I have to do is I have to do multiple experiments by varying tau m. If I change tau m, collect several times, changing the value of tau m, then the zero quantum coherence themselves will get cancelled out because of different phases. The randomization of the phases of the zero quantum coherences. So therefore, that is a trick we use to eliminate zero quantum. If you, of course, your mixing time is very large, like 1 second or something, if you put, then of course it will go away. But if you are putting a small mixing time like 50 milliseconds or 100 milliseconds, sometimes it may not go away. So in that situation, you vary the tau m randomly or systematically in larger number of steps. Suppose you do it in about 10 steps or 15 or 16 steps. For every scan, you change the value of tau m. For every scan. So if it is 50, 55, 60, 65, 70, if you do that, then what will happen is you remember for the same period of T1, then the zero quantum coherence can be cancelled out. So this is the trick one uses to eliminate the zero quantum one. Usually this is not a problem in large molecules because the large molecules of the T2 relaxation time is very small, even for the zero quantum coherences. Therefore, during the mixing period, it will automatically get eliminated. Okay, so therefore, this demonstrates a different choice of coherence pathway selection. Different combinations of phase cycles are indeed possible. So these two examples which I give you, how you choose different pathway. One case you choose double quantum filtering pathway. Other way you use the Z selection. So this is all done by the phase cycling, but the zero quantum does not go away because you use a different trick to eliminate that. During the mixing time, recovery of the Z magnetization of K spin causes transfer of magnetization to a dipolarly coupled spin L, let's say. Therefore, IKZ gives lambda IKZ plus 1 minus lambda ILZ. This is what I also schematically shown in the previous slide. So lambda represents the residual magnetization on the K spin and 1 minus lambda represents the transfer to the L spin. Okay. So finally, at the end of the mixing time, the density operator is rho phi is equal to minus 4 into this, the same partition, cosine pi j k L T1, cosine omega k T1. The final 90-degree pulse converts the Z magnetization into observable magnetization. This gives you 4 lambda IKY and this gives you ILY. Okay, 1 minus lambda, and the coefficients remain the same. What I have written here. Sorry, this is cross. IKY and ILY. So this is the diagonal peak and this is the cross peak. Is it possible to correct it into this ones properly?
No, then you can run in a wall.
Huh? I have corrected here, but I think it will remain there like that. Those ones.
उसको एक presentation mode में नहीं है.
Presentation mode. At the last you can do that, yeah. So the both of the diagonal and cross peaks have the same fine structure with in-phase components and peak shapes absorptive. Because you see both are in phase, IKY, ILY, both are in phase and they are absorptive because both are Y. So therefore you get in phase cross diagonal peaks and cross peaks in the things. Okay. See, I normally check many of these things, but since my laptop is not there, I could not check that.
Happens sometimes.
Ah.
I think they
But it is understood actually.
It's understood.
It is understood. You can't have two diagonal peaks. Both the diagonal peak doesn't make sense.
Someone must have noted it.
Yeah, someone might have noted it already.
But this is available, na? This is getting recorded.
This is getting recorded, yeah.
So they can cross check in the record part also.
Yeah.
Video part.
Okay. So in case of multiple spin systems with many dipolar couplings, the magnetization gets distributed through the network of spins because whenever there is an in-phase transfer, okay, this will always happen. Same was true in the TOXI. TOXI also K to L, L to M, M to P, things like that treatment because there is an in-phase transfer. So here also it is the same thing. With many dipolar coupling, magnetization gets distributed through the network of spins. Explicit calculations of polarization transfer during the mixing time through cross relaxation or chemical exchange have been discussed in the previous classes. Okay, this we have discussed in the previous, as I said in the previous lectures, and we provide the final result of the intensities of the diagonal and cross peaks. Exchange cross peaks and cross relaxation cross peaks are separately seen in the NOESY spectra. You see, you will also get this exchange relay. Cross relaxation, dipolar coupling relaxation is one thing, cross relaxation. But if there is chemical exchange in the molecules, there is a chemical exchange. Then also it causes the transfer of magnetization. And that also will show up in the NOESY spectrum. IKZ to ILZ, when it goes, it can either go through cross relaxation or it can also go through chemical exchange. If there is a chemical exchange happening, then it can go there. Then it is not distance dependent, of course. Then it will depend upon the exchange rates. Therefore, in the NOESY spectrum, we will see those also. You will see exchange peaks also. And that calculation has been done. This is the overall result for all of those diagonal and cross peak intensities in NOESY spectra. Whatever the mechanism is, so you will have the diagonal which is coming down with the time and the cross peak will go up and then decay with time. In the case of cross relaxation, then of course this will be dependent on the distance over a period of distance, then it will decay. And in the case of exchange, it will depend upon the exchange rate. How the exchange, if the exchange is zero, then of course there will be no peak, and exchange rate is increasing, you will have the cross peak intensity is growing. Then of course, because of the decay of this magnetization, it will also decay. Okay. Now these explicit calculations have been done for a symmetrical two-site exchange, and that is considering a two-site exchange A to B with equal populations at the two sites, equal spin lattice relaxation rates, and equal transverse relaxation rates. The intensities of the diagonal, which is alpha AA and AA and ABB, and cross peaks AAB and ABA are given by the following equations. These I have given the results only here. This explicit calculation we are not. I have not shown it here. So this is the diagonal peaks are half 1 plus e to the minus 2k tau m into e to the minus tau m by Tn, T1, and k is the exchange rate. Okay. And the cross peak intensity is half 1 minus e to the minus 2k tau m divided into e to the minus tau m by Tn. Now obviously, if you see if tau m is equal to 0, then the cross peak intensity will be 0. Right? So this is e minus 2k. If k is 0, then this term will be equal to 1. 1 minus 1, 0. Then of course you will have no cross peak. But the diagonal peak will be there. As the exchange rate increases, then you will have the peak intensity building up. And then after a certain time, the relaxation takes over. And e to the minus tau m at T1, initially it increases and then it starts decreasing because of the T1 relaxation. That's why that sort of a curve will also appear in the case of exchange as well. And this appears, and these are separate peaks in the Nosy spectra. The exchange peaks will be different than the dipolarly coupled peaks because the exchange happens only between two kind of spins. It is the NOE happens between various kinds of dipolarly coupled networks. So therefore, these peaks will be seen separately in the Nosy spectrum. Now you can take a ratio of the diagonal to cross peak intensities, that is AA by AAB, that is 1 plus e to the minus 2k tau m divided by 1 minus e to the minus 2k tau m. And if you have the short mixing time, then actually you can exponentially make it as simple this one, and compared to T1, this will simply become 1 minus k tau m divided by k tau m, because you expand this exponential term as 1 minus 2k tau m, etc. So it's power series. So you will simply get 1 minus k tau m divided by k tau m. So therefore, by measuring the ratio of the intensities of the diagonal and the cross peaks, then you can actually estimate the exchange rate. So this is very important information. Monitoring the intensity ratios as a function of tau m, you can calculate the exchange rates. In the case of cross relaxation, the cross peak is proportional to cross relaxation rate times tau m, and this is proportional to 1 by r to the power 6. This is proportional to 1 by r to the power 6, and therefore these intensities can be used to calculate the distance between the nuclei A and B. Okay, this allows estimation of interproton distances in complex molecules. Therefore, from the Nosy spectra, you get two types of information. You get the distance and you get the exchange rate whenever exchange is present. Okay, now here is an example. You see the molecule. This is a terpene molecule. I took it from this book here, Timothy Claridge's book. So all these various protons are indicated here. Okay, and their individual assignments are also given on the top. Okay, now what are the red and the black ones? So these ones will be the NOE peaks. This is the small molecule. Small molecule, you remember in the Nosy spectrum, the NOE will be negative in the Nosy spectrum. For large molecules, NOE will be the same sign as the diagonal peaks. Okay, so here we have all these red peaks are the NOE peaks. Okay, and therefore you can see from here, you take this extreme one here. From A, you are seeing the cross peak. Where is A? A, where is A? Here, in the molecule. Here. Now this A is showing a cross peak to this fellow. E. Okay, let's look at this. This one is here. This one is E. A is showing to E. Okay, that's here. E and F. And is also showing to F.
Yeah, it is both are there, very close, na?
They are both close.
Those are very close.
Yeah.
So they are actually orthogonal. See, this HA and this are they are not.
They are orthogonal. E and F close.
Both are getting close.
Both are getting close. So, and then you also see to this. Which one is this? That is this here. And this one is your N and M. No, sorry. Yeah, N and M.
CH2 is there.
That's here. That's here.
That is also getting.
This is also clear.
Yeah.
And then you also have here. And this one is this. And this is P and Q. Where are P and Q? Those are here.
Yes.
Here. And you are seeing to this also.
Yeah.
So therefore, you see how so much of structural information is present in this.
3D structure, some of
Yes.
those two protons are equal to axial, so they
They are coming closer. So from this one particular distinct one, you can see these peaks. And this one also you are seeing here. And what is this? This one is H2O. Okay, now this is an exchange peak. So that is showing to water.
Yeah, that is the hydroxyl.
Hydroxyl group. B is hydroxyl.
Yeah.
Hydroxyl is exchanging with water. So therefore it is an exchange peak. Yeah. So then you even see that in all of those, similarly C also. C also is, yeah, this one. And this is here also. All of those hydroxyls are showing exchange peaks. to the water. There's along this. So therefore, this is such a useful information there. Distinctly, you can identify which are the exchange peaks, which are the NOE peaks, and from the NOE peaks, we can calculate the structure of the molecule. A big analysis may be, this may be an exercise. This may be an exercise for the students to analyze this, all the peaks. Take this molecule and identify, here the assignments are already given there. But typically, when you are recording the spectrum, you may not know the assignments. But actually, these NOEs will provide you the assignments. You can use this to obtain the assignments. So therefore, this is an extremely useful tool to determine the structures of the molecule, and you can get the assignments from here. See, there is this one. So C and this is also exchange peak there. C to H, is it? This is it.
C to H. Yeah, there are two hydroxyl groups. No?
There are two hydroxyl. Yeah.
Close. 1,3 hydroxyl. There will be.
Yeah. Oh, C is here. C is here. These are close. Yeah. So they are showing exchange peaks. Right. Between themselves. So such a useful structural information can be obtained from the analysis of the noise spectra, which contains both exchange peaks as well as NOE peaks. Okay. So now we move to the next experiment, which is called the 2D ROSI experiment. So when do we do 2D ROSI? Our ROSI experiment we do in small molecules when you get the zero intensity. Of course, typically you do it in small molecules. Often in the noisy spectrum, sometimes you may get zero intensity. And you may think that, okay, the distance is very, very large and therefore the peak is not there. But that is not the case. It may be because there is omega tau c is such that it is close to 1 and you will have a NOE intensity close to 0. So in such a situation, it is the 2D ROSI experiment becomes important. The pulse sequence of this is very similar to that of the TOCSY. And it is except that the spin lock power here is much less than it is in the TOCSY. The TOCSY, the spin lock, the RF power which is used for the B2 field is much less. And the transfer of thing happens through the relaxation here, not through the coupling, because the power is it's not like a strong coupling Hamiltonian, because the power is small. Since the power is small, it is not a strong coupling Hamiltonian. It is still a weak coupling Hamiltonian. So you hold this using this usual Solomon equations. We can calculate the transfer of information of the magnetization is transferred from one spin to another spin. So IK, I'm just giving the results here. Okay. So IKX tau m at the end of the tau m period, it is 1 minus tau m by T2 sine omega k T1. So the pulse sequence, I think now you understand the pulse sequences very well, because the 90 T1 spin log T2. So the T1 is what happens at the end of the T1 is what is written here. IKX tau m, so is at the end here before the T2 detection. So IKX tau m 1 minus tau m by T2 sine omega k T1 IKZ naught minus sigma tau m sine omega L T1 ILZ naught. Okay. Now this will be the diagonal peak and this will be the cross peak. Why do I say this? Because this is the sigma here, the cross relaxation rate. The cross relaxation is connecting from one spin to another spin. Okay, and in a homonuclear case, of course, KZ naught and IL naught would not be the equilibrium magnetization. The I naught, KZ or LZ, they are the equilibrium magnetization. Therefore, with the homonuclear case, they will be the same. But in heteronuclear case, KZ naught and LZ naught may not be the same. So you will have different numbers over there. But the sigma is the cross relaxation rate, which will actually tell you this will be the cross peak and this will be the diagonal peak. The ILX, similarly, it will be, and also you have omega L here. See, this also indicates you that this is a term which is relating to the cross peak. And this is omega K here, which is the diagonal peak. So ILX similarly will give you the diagonal peak here and the cross peak there. And they are both determined by the tau m as well as the cross relaxation rate sigma. Now, One important difference, this is the calculations I've gone through, all of discrimination of cross-reaction and chemical exchange peaks in large molecules. Of course, Rosie, we have already I probably have it in the next slide. Here, and I will come back to that one later. The Rosie you do, rotating frame over effect, this is the calculation of the ROE effect. See, this is always positive. Okay, ROE is always positive. This is against the correlation time here, omega naught tau c. Omega naught tau c correlation time. So the NOE goes from minus 50% to minus 100% or minus 1, 0.5 to minus 1. And it goes to 0 at this point. At this point, there is no NOE. Whereas the ROE is always there. ROE is never 0. Therefore, for small molecules, it is most desirable to do ROE experiment. So you will not miss any correlations. Okay. Now you see here, this calculation has been done for various kinds of situations. Omega naught tau c much smaller than 1, omega naught tau c equal to 1, omega naught tau c larger than 1. Okay. And what is given here is the sign of the peak for the different situations. Earlier we already saw for omega naught tau c is equal to 1, diagonal peak is positive and the cross peak is negative. We saw this on a particular example. Okay. And in the Rosie, that is the same. Diagonal peak is positive, cross peak is negative. Omega naught tau c approximately equal to 1. The diagonal peak is there, but the cross peak is 0. And the diagonal peak is positive, cross peak is negative. Okay, this is no difference here. Most interesting thing is this. Omega naught tau c much larger than 1. This is a large molecular situation. This diagonal and cross peak are both positive in the Rosie spectrum. Okay. And in the Rosie spectrum, diagonal is positive, cross peak is negative. So therefore, when you are dealing with a large molecule, the Rosie spectrum will not allow you to figure out which is the exchange peak and which is a cross peak. So therefore, that becomes a limitation there. You will have difficulty in identifying which is an exchange peak and which is a NOE peak. Whereas the Rosie will tell you that. Rosie will tell you because the diagonal peak is positive and the cross peak is negative in the large case, in the large molecules as well. Therefore, this discrimination will tell you. And if there is a chemical exchange, then diagonal peak is positive in Rosie, and it is positive and positive in the Rosie. But this will allow you the discrimination as to in large molecules that whether you have chemical exchange or not. Okay, so that is an important benefit in large molecules. Okay. Okay, so this I already showed you large molecules and fields, how you can measure this. I think I finished with this. Now, so actually I finished only 13 now, right? Lecture number 13. Okay, go to 14. We may not be able to finish this 14. So we will start and then
Stop. Yeah.
So we have here two-dimensional heteronuclear correlation experiment. So far we are dealing mostly with homonuclear cases. Okay. Now we want to now take up heteronuclear cases. We will make a beginning here. So the most detailed things you can go up in the next one. The heteronuclear case, coherence transfer can be affected between two different types of nuclear species, say I and X. Such experiments are referred to as heteronuclear correlation experiments. A variety of heteronuclear experiments can be designed since the RF pulses can be applied selectively to either species and heteronuclear broadband coupling can be incorporated without any constraints, which is a simple thing. Okay, so heteronuclear experiments have particular advantages. What are these? Increase the sensitivity of indirect detection as evidenced in the inept pulse signal. This we already saw in the inept. When we have proton, the magnetization is transferred from the proton to the carbon. That is the inert, and you can see the enhancement in the sensitivity. Possibility of unraveling high resonances by exploiting the chemical shift of the S spins and vice versa, right? So because you establish a correlation between I and S. Therefore, if there are two peaks at the same I, if they're coupled to different S spins, then you can separate them on the S spin with the S spin correlation. Correlation of chemical shifts of different nuclear species would facilitate assignments in complex systems. Therefore, when you go to larger and larger molecules, you need to do heteronuclear experiments by necessity, actually, not just by choice. In most cases, one of the two nuclear species are rare nuclei, such as C13 or N15, and the other nuclei are usually more sensitive species, such as proton, F19, etc. Okay. Let's look at the heteronuclear Cozy experiment. This is the direct, simple extrapolation from the homonuclear case. Okay. So simple heteronuclear Cozy experiment. Notice here we will not have anything like a diagonal. Okay. So we are exciting the proton, let's look at the pulse sequence. So we have on the proton channel and the X channel. The proton channel, we have two pulses, 90, T1, 90, and the X channel, we only have one pulse, the 90 degree. So what will happen when I excite with the 90 degree pulse on the proton? In the transverse magnetization here, I have created proton magnetization only. I start with the HZ, homonuclear, the proton Z magnetization. Therefore, I will here have HY or HX, right? So this is probably HY. If I apply X pulse there, I will get here an HY. During the T1 period, therefore, it is the proton which is getting frequency labeled. I will get HY cosine omega T1, okay, omega H T1. The proton frequency will evolve during this period. And it will also generate antiphase magnetization at this point. HY will generate, I think the calculations are there probably. No, okay, no. I skip the calculations because it can be very simply done. So you have HY here, HY cosine omega T1 minus 2HX CZ sine omega T1, right? So it is the coupling evolution as the result of the coupling evolution. The chemical shift evolution will anyway happen, cosine and sine, and after the coupling evolution, you generate an antiphase magnetization here, and then when you apply simultaneous pulses on the proton and the X nucleus, you transfer magnetization to the X nucleus. And therefore, I've written only the relevant part of the density operator. So here I get here 2xy hz. I started with hz here, chemical shifts of the protons here, and I have the 2xy hz chemical shifts of the X nucleus at this point. Okay. Chemical shift of the X nucleus. So I detect here T2. What do I detect? I detect the X nucleus. Therefore, during the T2 period, I will have the X chemical shift. So therefore, along the F2 dimension, I have X. F1 dimension, I have proton. The signal to noise gain is gamma H into gamma X to the power 3/2 because this is the excitation and this is the detection. It is proportional to 3/2 of the detected nucleus, proportional to the gamma of the excited nucleus. Therefore, this is the signal to noise ratio. Now, how many peaks you will get? You will get peaks, one peak for every correlation. So if there is a one proton coupled to one carbon, of course you will have one peak here. There is nothing as a diagonal here, okay? Because on one axis I only have the proton, other axis I have the X. Therefore, I only have cross peaks. In this situation, I will only have cross peaks. But of course, the coupling information will be present. So if I take any of these peaks, I will have the same sort of a cozy type of pattern here, plus minus minus plus, plus minus minus plus, and this separation will be JXH, and this separation also will be JXH. So it's very similar to the cozy, except that I don't have the diagonal, I only have the cross peaks. Okay, so this is what happens if I do a excitation of the proton and I detect the X nucleus. Now indirect detection. Indirect detection, what I want to do is, I want to detect the proton, but I want to excite the X nucleus. So therefore, what I will have to do, I will have to put two pulses on the X channel, but one pulse on the proton channel. So I put X90 T190 on the X channel. So therefore, I create here X magnetization. transfer Zach magnetization. So during the T1 period, it will be chemical shift of the X nucleus. And then I transfer this to the proton at this point, therefore I will have 2HYXZ. 2HYXZ, this is antiphase. This is antiphase, and this will evolve during T2. Therefore, I detect here the proton magnetization. Therefore, what will the signal to noise be here? It is gamma X into gamma H to the power 3 by 2. So which is better? Gamma H to the power 3 by 2 is better than gamma X to the power 3 by 2, right? Therefore, this indirect detection have an advantage of sensitivity. Signal to noise ratio will be better in this situation. Therefore, we will rather excite the X nucleus but detect on proton. Therefore, this is called as indirect detection. But then what will I have? I will have the F1 dimension, I will have the X chemical shift. On the F2 dimension, I will have the proton chemical shift. The fine structure will still be the same. You will still have the same fine structure. Okay, plus, minus, minus, plus, that will be the same. But you have an advantage of sensitivity by this factor. Now, what we do is, we don't want to have this splitting, because these are XH splittings are very large. See, in 100 Hertz, 150 Hertz, why do you want that separation? I mean, that is unnecessarily confusing. We don't need that information. That coupling anyway doesn't vary. It is not structurally relevant either. So we don't want to have that coupling information. So what do we want to do? If we have that sort of a situation, we cannot decouple also, right? Because they are plus minus. When they are plus minus, we cannot decouple. So therefore, we need to do something like an inept refocusing. So we do the same thing here. Until this portion, it is the same as the previous case. Same indirect detection here, indirect detection. But then afterwards, we put this period spin echo, tau 180 tau. But the tau is now 1 by 4j. Because this coupling constant is known. This coupling constant is known very well. So therefore, we put that coupling constant. According to that, we put 1 by 4j. So during this period, so here I get 2HYXZ. Chemical shift does not evolve. Proton chemical shift does not evolve because I put a spin echo. 180 pulse refocus is the proton chemical shifts. It only evolves under the coupling. 2HYXZ will give me HX at this point. So in phase proton magnetization at this point. Now since it is in phase, during the T2 period, I can decouple. I can decouple the X nucleus. Therefore, I decouple here the BB decoupling, broadband decoupling. So therefore, what will happen is, along in the 2D spectrum, the sensitivity is the same as gamma S to the power 3 by 2. X will be along the F1, H will be along F2, but the splitting along the T2 dimension is removed. So splitting along this dimension, but I will still have the splitting along the F1 dimension. That splitting will be there. That is still evolving here. Coupling is evolving here. Therefore, that coupling will result in a splitting because of the XH coupling. Now, if we did the same thing with a direct detection, this is the equivalent of the first experiment. You start from proton, transfer here to XYXZ, refocus here, this X magnetization to this point, you get XX, and if you detect here, then you have T2, and the BB decoupling you can do because you have not refocused it. Once you refocused it, you can do broadband decoupling of the proton. If you did this, then what will have the same structure as in the very first slide, but now the splitting will be there along the F2 dimension. JXH will be there because here H, okay, sorry, H is here. H is here. H is F2. X is, sorry, okay, here it is, this is F1, okay, this is T1 here. So, that's what a mistake. This slide has a mistake. So this is 90, you are starting with proton. So along the T1 period, I should have proton. I think we stopped it. This is wrong. So this here will be F1 will be proton. F1 will be proton. F2 will be F2 will be X. Okay, F2 will be X. Actually, this picture is wrong. This experiment is fine, but that picture is wrong.
I think वो copy paste में है.
हाँ, ऐसा कुछ हो गया होगा, तो गड़बड़ हो गया इधर.
Yeah, F1, because hydrogen is there in the F1. ना?
Hydrogen is in the F1, so therefore F1 will have, here it should be proton, and here it will be X. Here it will be X, and so where will be the splitting? The splitting will not appear along the F2. ये भी तो गड़बड़ है. This will be like this. So let's see in the previous one what was there. So T2, yeah, T2, okay, this is fine. This is fine. So here the T2 proton is collecting T2, this is fine. Proton is along the F2 and X is along F1, and you are decoupling the along the T2 dimension. Therefore, there is no splitting along this dimension, you only have splitting along F1. This is fine. Okay. Now here you are decoupling in the F2 dimension, there will be therefore no splitting here. It should be like this only.
Yeah.
It should be like this. And
Because now your the axis changed, na?
axis is changed.
So that's why.
Ah,
Put F1 this way, F2 other, na?
yeah.
Then this is correct.
Yeah, yeah. So if I put here, if I put this spectrum here, so this is my F1 and F2. So, and the F2 is X. F2 is X. F1 is H. And where is the splitting? Splitting is along the F1. Therefore, I will have peak like this. So this will be the structure of the peak in this spectrum. Okay. So this and for this portion remains the same. Gamma h to the power 3 by 2. That will be the same. Okay, now I think this maybe we will have to stop at this point. We take advantage of both of these things and then we do this. क्या ये कट पेस्ट में गड़बड़ हो गया है?
Previous slide में.
हाँ, इसमें?
This previous slide.
Yeah. This one?
Okay.
X is F1. This is correct, right? X is F1. This is X here. So X is F1. Detection is proton. Therefore, detection is proton is F2. And during the T2, we are decoupling the X. Therefore, there should be no splitting along the F2. And the splitting will be there along the F1 dimension. That is here. So this is correct. So this is basically cut paste हो गया. This spectrum, this figure is basically cut paste. तो उसमें गड़बड़ है.
वो X and H में interchange.
Yeah, X में interchange हो गया.
Okay, so देखिए participants का response. Everybody is.
I have to immediately correct these slides. Whenever
2-3 points, some mistake was there, you can maybe correct it.
Yeah.
So what you do not share the final slides today. So जब next आएंगे ना,
Yeah.
तो corrected slides को share.
That is better, sir.
That's
So
better.
comfortably correct it.
I agree.
And next,
But I cannot do it until I get my laptop.
because next lecture is Wednesday only. By the time I
Let
think.
me do it here.
Ah,
You can do it here.
we can do it here also.
So then next week we'll do it.
Ah,
Or you can do it now also.
yeah, maybe we can.
Many, one that slide and this slide. These two slide only major correction, no?
Yeah, no, only one slide. The previous slide that was fine. Which one was?
One slide.
Oh, cross and diagonal.
Diagonal. Yeah, diagonal को cross लिखने का. We can do that right away. Why not we do it here?
You can do comfortable, sir. Lecture.
Yeah, so
But
Okay, now.
question you just ask them.
So we stop here now.
Stop here, then we can correct it.
Yeah.
After closing the.
Correct.
So participants, so if you have any question?
Sir, you can ask participants.
Yes.
Yeah. So you have any questions? Everything is clear?
Friday class नहीं.
Or There is no class on the
Yeah,
Friday.
participants, if you have any question, you can ask. And one more thing, this Friday, there is no class because government has declared holiday because of Ambedkar Jayanti. So Friday, there is no class. Okay, so our next class will be
Next week.
next Wednesday.
At 3:30.
That is circulated
Okay.
already.
One was showing us any reference.
Sir, any reference book for this part?
You can give the reference book of those men. Richard asked.
Yeah, shown some.
I shown the Claridge book I shown. Reference book is there in the slide. That book is indicated in the slide.
Is check the slides.
Yes,
Like where I took the picture from. Or somebody asked for the reference book, is it?
Yeah.
Okay. So it is Timothy Claridge. That is the book which from some pictures I have taken from.
Okay, fine. You can write it, check the slides.
Yes.
One of the slides is.
मतलब slide share करेंगे तो मिल जाए.
Yeah.
Okay, sir.
Okay, indeed.